দেখো আমি স্টেপ বাই স্টেপ একবার বলে দিই, না তো আবার ওর হবে না। So once more from beginning, what is elasticity? Elasticity is the property of matter. Okay, GPM. This comes under the category of general properties of matter. In short, we write GPM. Under GPM, what you have to study in class 11? Elasticity, surface tension, viscosity. Okay. Elasticity, that is mechanical properties of solids, we are going to study now. What is elasticity? And why do we have to study elasticity? That is important. When you are constructing building, elastic property of a substance is very important. Even a rail line, when you are being an engineer, you are appointed to observe the proper installation of all those things. Then you have to know where you are placing it, what is the stress and strain of the matter below the line. Like one example I tell you, if somebody asks you question why the height of Mount Everest or the maximum height of mountain is limited, why it cannot be more than 10 kilometers. Okay. Similarly, what is buckling? When you are constructing bridges, that bridge maximum depression at the middle can be what amount and what kind of material will prevent any damage or accidents while constructing a bridge which is at a great height above the earth's surface. So elasticity plays an important role over there. Even there are two terms, elastic fatigue and elastic after effect, we need to know. In this chapter on mechanical properties of solids, elasticity will study all those things one by one. It is the property of a rigid body or property of an object by virtue of which it will regain its original shape and configuration back when the external deforming force is removed. What is that? Just suppose there is a cylinder, some load is applied at the top of the cylinder. Then what will happen? Its length will be diminished. If you take length is equal to L, some load is applied at the top, then what will happen? The length will be reduced. What about the area of cross section? Obviously there is an effect on the area of cross section. Area of cross section will increase. Okay, but initially we will not consider the effect of both together. That also definitely we will consider, but not in the beginning. If we keep a rubber band here or a steel rod, and if you apply tensile force, what is tensile force? Lengthwise the force you apply, that is called tensile force. The tensile force be equal to F. Then what will happen to this rod? The length of the rod will increase, isn't it? There will be change in its length. This length will not be double of it. Even in some cases the increase in length is not very considerable amount. Okay, but this change will be there when it is subjected to external deforming force, and we are going to work on it initially by assuming that when you apply this tensile force, the area of cross section remains the same during the process. We have applied the force. Before application of the force, whatever the area, after application of the force, it has the same area, that is equal to A. Now this lengthwise increment will change the volume also, isn't it? But one factor will remain the same, that is mass of the solid. Mass of the solid will not change. Now this is one example where tensile force is applied. I am taking another example. Suppose you have taken a ball which is under hydrostatic pressure. If it is immersed, if it is taken at certain depth below the water surface, then this is subjected to water pressure from all sides, that you know. Suppose you are changing height of the ball, depth of the ball. Initially it was at a height h. The height is changed. It is taken up or taken below. If you have taken it below, then what will happen? There will be change in its volume, isn't it? If this ball is taken at greater depth, the volume will be decreased. Am I correct? Let that volume become V minus delta V. Volume will be decreased. This is the case of hydrostatic pressure, and volumetric change is there. Okay. What another kind of change we can observe? Suppose there be a cube. So what we observe here in this case? We observe change in length by applying external deforming force. What do you observe here? Change in volume by applying external deforming force. Ball is taken at greater height. Is there any other change possible? Yes, it is possible. Suppose there is a cylindrical rod or a string. This string is subjected to twisting force, which will give the cylinder a twist. For example, if I show you by taking a string is there. When the string is given some torsional, some torque this manner, then what will happen? If you give some torque, if you apply some torque, then it is distorted this manner. And then if you remove the external torque, it will come back to its original position. Same manner here also. When you are taking the ball at the same height, its volume is not going to be changed again. When you are removing the external deforming force, this is not permanent. This is when you have applied the force, the change is observed. But as soon as you remove the force, then it will come back to its original state. This is elasticity. As soon as the deforming force is removed from here, the twist, if it is being twisted, it will come back to its original state. Similarly, this I can discuss with you in another example. Suppose there is a cubical shape over there, an object. If we apply tangential force, what kind of deformation you observe here? If a tangential force is applied here, what kind of deformation you observe? The base is A, B, C, D. What will happen? Just let us consider this change of this surface only. What is happening to this? This will move forward. Okay. This one also will move forward. This way it get distorted this manner. Okay. So this deformation is produced. This is called shearing strain, and this one is called longitudinal. This change of length is called longitudinal strain, and change of volume delta V, this is called volume strain. Okay, all these are being changed. Similarly, let us perform another experiment where there is considerable change in the area of cross section. Suppose this rod has area of cross section A and its length is equal to L. Suppose its length is changed to L plus delta L and area is changed, area of cross section changed by delta A. Or suppose diameter or radius was R, now radius is changed to R minus delta R. But length is increased. Length increased to what? L plus delta L. Then how many changes do you observe there? There is change in length, delta L, and there is change of surface area. Okay? We will be discussing mainly changes in these four cases. Where there is tensile force, change of length, where there is volume stress, change in volume, where there is shearing stress, that angular position is changed of a line fixed in it, and there is lateral strain where with the change of length area is also changing. These topics we are going to study by defining some terms over there. Those are basically known as stress and strain. Let me define those two terms here first. What is a stress? Suppose this object, let me explain, no need to write definition now. Suppose there is an object, it is subjected to an external force F over the area A. Okay? By Newton's third law, if a force F is applied, equal and opposite amount of force will be developed in it. Direction is not changing, in the same direction only, the same force will be developed in it. The stress will be defined as stress equal to what? Force by A. But when you are stating definition of stress, it is actually the internal force of reaction developed, internal force of reaction developed per unit area. This is called stress. Okay? So internal force of reaction, you are applying a force here, that's why reaction force F will be there. Any object when subjected to some force, reaction force will appear, isn't it? So that's why it is called internal force. Due to its own property, the object offers the same amount of force. This we have the experience. When you are applying a force F here, same internal force of reaction will act on us. That per unit area is called stress. What is unit of stress? Unit of stress will be Newton per meter square. Dyne per centimeter square also there, but we use mainly this thing, SI unit, Newton per meter square. Now this stress, as I told you here, this stress can be mainly three types of stresses we are going to discuss. Number one, longitudinal stress. Then longitudinal, then there is volume stress, not longitudinal, it is volume stress. Then there will be shearing stress. Okay? What is longitudinal stress? This diagram I have drawn earlier. There is a rod of length L and area of cross section A. It is subjected to a deforming force both the way. Otherwise, what will happen? If you don't apply force both the way, it will have acceleration. If you apply in one direction, isn't it? We don't want it. We want to elongate its length, or we want to compress. There may be compression, may be elongation. This time it is shown elongation. Length is L plus delta L. So what is longitudinal stress here? Longitudinal stress will be what? Internal force of reaction how much? If you have applied force F, internal force of reaction F only, that divided by A. This is called longitudinal stress. You have applied longitudinal force F. On what area it is acting? Area of cross section only. What we have defined stress? Stress is internal force of reaction per unit area. What is area of the rod? That is A. So there will be F by A. Longitudinal stress.
So the resultant force 0 है तहारी elasticity or stress एंगल आशुपे.
Resultant force, when we apply external force, there will be a force. This force will not be 0. If we have applied external force, the action force will be there. It will not be 0. If it is 0, then that is the case of dynamics of rotational dynamics or Newtonian mechanics. Here it will not be 0. Okay? If you have applied force, there will be a reaction force. We are working on that. Okay? Now, volume stress is what? This ball of volume V say subjected to let a ball of volume V be subjected to a pressure P. This is called hydrostatic pressure. I have taken hydrostatic pressure just for better understanding. Hydrostatic pressure is P. Let the pressure be increased by delta P, so that the volume is decreased by del P. How do you increase the pressure? You take it greater depth, then only pressure will be increased. So what will be volume stress here? Can you tell me? Stress is what? Force by area. Force by area is pressure only. So volume stress going to be del P. Okay. Force by area, in case of hydrostatic pressure, force by area is what? Pressure. So that is only volume stress. Increase in force when force is being increased, no? Because if you have taken at a depth h, then taken at some other depth h dashed, the object is taken at some other depth h dash, then force is increased. So pressure is also increased. So that increase in force per unit area is increase in pressure. That's why we will be writing volume stress as delta P. So in both the cases, in longitudinal stress or volume stress, these kind of stresses are referred as normal stress. Remember this. Why normal stress? Because they are applied perpendicular to the object under consideration. Here pressure due to water acting all the way, no? Pressure acting all the way. Okay. So volume stress you have understood. Now let us learn shearing stress. In case of shearing stress, the stress will not be normal. This time it is going to be tangential. We have to apply some tangential force and then so shearing stress we draw the same cube we have taken earlier. You can see that this cube only we are going to take. Okay, this cube, or we draw a diagram here. This cube is subjected to, or we are taking the cross section of the cube. How it is getting deformed you have understood? Because when subjected to tangential force, this force be F and area be A. Area of what? Area of the top surface be A. Then what is the value of shearing stress over there? That force by area only. The definition is force by area. That is called stress always. So tangential stress will be, or that is known as shearing stress, that is going to be what? That force applied by area. Area of which part? Area of this upper part. I mean the free surface is area. So shearing stress is going to be F by A. These three stresses we will keep in our mind. One is longitudinal, number 2 is volume, and number 3 is shearing 1.
So free surface meaning?
Free surface means top surface here. Not free actually, that external force we are applying. Okay, no other external force is there. Only that force F we are applying. Just a normal cube is there and we have applied force at the top surface. The top surface we have referred as free surface. I mean not subjected to any other external force. Okay, only this force is there. So shearing stress is F by A. Now we have to learn another term that is called strain. What is strain? Strain is defined as ratio between these two things: change in dimension by original dimension. That is called strain. This class I am taking, which is based on new syllabus, new NCERT book, CBSE, according to CBSE syllabus what is given, that only I am telling you. Okay, not taking any reference from old books, from the new syllabus what is there. So strain is what? Change in dimension by original dimension. Does it have any dimension? This dimension and that dimension different. Dimension analysis you did. It is a dimensionless. This strain is a dimensionless variable. Isn't it? It depends. It changes from one object to another object. So change in dimension by original dimension, it is neither have any unit nor any dimension. So in these three cases, let us write the value of the longitudinal strain first, then volume strain, and then shearing strain. How will I write longitudinal strain? What is the change of dimension? If it is elongated or compressed, similar thing, just change. So longitudinal strain will be delta L by L. Am I correct? Change in length by original length. And then what is volume strain? This object's volume, here it is V, and what is the volume here? Hydrostatic pressure acting there also. But here pressure will be more on this object. So what is the volume strain over there? This volume V and this one is what? V minus delta V. So how do I write volume strain? Say delta V by V, simply delta V by V. So write volume strain is equal to delta V by V. Okay? And then we will define shearing strain. Shearing stress is defined F by A. Shearing strain will be here. The result of this tangential force which you have applied will deform the object. This shearing force will do what? We can understand with the help of this book. If you have applied a tangential force, what do you observe? The book get deformed this manner. Book is getting deformed this manner. What manner? Tangential force is there. A line fixed in the body, it is getting inclined now. Okay? This angle of inclination made by the line with the initial position is called shearing strain. So we will define strain here. So what is happening there? If this one is say PQRS, this cross section, what happened to this cross section only? You try to understand. It get deformed this manner. You agree or not? It will be deformed this manner or not? It will be deformed this manner. This is not only this surface PQRS. It will be for the back surface also. So we will be defining this angle as shearing strain. So shearing strain is what? That will be denoted by theta. How do I write its definition? It is the angle between a line fixed in the rigid body or in the object between its angle between a line fixed in the object with the initial position, with its initial position. So this elasticity is such a vast topic. In master degree course, students of branches of physics and mathematics, we have studied a subject which is known as elasticity and plasticity. Okay. S. N. Bose, no? He did his masters in this subject, elasticity and plasticity. That time it was being developed. Now it is developed. It has wide application in civil engineering and some other engineering also. I don't know much. I know it is there in civil engineering. It's a very important topic over there. And the topic in master degree also, physics, mathematics, fluid dynamics. It is the, pillar, this topic. Okay, elasticity is a very important topic. So we cannot study everything on elasticity today. Like there is a limitation. We are assuming this base, this is the base of the cube, no? This cube base is not changing its position. This is our limitation of class 11 physics. We will learn where the base is not being changed due to the application of tangential force, only it is getting deformed in that manner. Okay, line was fixed in the rigid body. Which line was fixed? PS. Now it is gone to PS dashed. Which line was fixed in it? QR. Now it is gone to QR dashed. Similar is the case for other parts, but lower position PQ is not changing. This is our limitation here, I told. And this angle theta will be referring as shearing strain. Clear? These three, stress and strain, I think none of you have any problem. I told you mainly we will be discussing these three. In addition to that, we will learn lateral stress, lateral strain and longitudinal strain. Their ratio also, that is called Poisson's ratio. But later. Wait. Here, this theta only, we can derive a formula, wait for that. Here definition I told you, it is the angle between a line fixed in the object with its initial position. Okay, if you are fond of formula only, let me try to derive. This is the vertical side of the cube, look at the board. Then, what is the displacement of this line? Linearly theta, and lengthwise how much? Delta x. We are going to account for this theta. So can't we write, since theta is small, elastic property is not true for large angle or large deformation. There will be elastic limit also. Our next topic is that only. So this delta x is small. Since theta is small, can't we write theta as tan theta or sin theta? This is equal to what? Delta x by b. Therefore, shearing strain, this is our formula now, delta x by b. And remember, when you are going to use it, this theta always should be expressed in radian. In all our calculation, it will be in terms of radian. Okay? So everything is clear about these two, about these three, stress and strains. Okay? Now we are going to learn one empirical law. Why empirical? That you will realize. That is known as Hooke's law. Let us learn it. Hooke's law by Hooke and Crook. Hooke's law. Achha, every object has elastic limit. This Hooke's law is regarding elastic limit. I mean, not regarding elastic limit. This Hooke's law will work within elastic limit. Just before we go for any formulation, any graph, all these things, I tell you, one elastic substance is there, we are increasing its length. Elasticity property states that it will come back to the original state if the external deforming force is removed, isn't it? But if it doesn't come back to its initial state, you have deformed in such a manner that permanently some strain is produced in it. Then it is no longer elastic. Rubber band, when you are increasing length, up to certain limit, it will come back to its original length. If it is more, then you will observe that permanently its length is increased. Isn't it? Permanent diameter of that rubber band only, you think? No. I mean, not like steel bar. Steel bar also it will be like that. If you go beyond elastic limit, then some permanent deformation will be produced in it. I mean, no longer it behaves like a elastic substance. Up to maximum deformation what can be produced in it, that is called elastic limit.
So elastic limit के लिए physical quantity.
It's a physical quantity, you will realize. Within elastic limit means we can put the limit as 16 Newton for this rod. This is the elastic limit. Beyond 16 Newton if you go, then it will be permanently deformed. Okay? So within elastic limit means the maximum value of deforming force up to which the object can show elastic behavior when the deforming force is removed. Okay, that is called elastic limit. So Hooke's law is regarding that only. Within elastic limit, the stress developed in an object is directly proportional to the strain produced in it. Okay? Within elastic limit, you should be practicing with me with pen and paper. Okay? Within elastic limit, stress developed in an object is directly proportional to strain produced. So, stress by strain is equal to a constant. Okay? If you have taken stress as y and strain as x, suppose you are taking stress as y and strain as x, then what will you get? Y by x equal to a constant, that is y equal to mx. You all have the idea of this straight line, no? You can plot then y equal to mx. If this is the relation within elastic limit, what will be the stress versus strain relation? It will be a straight line, isn't it? So graph will be like this within elastic limit. This is strain and this one stress. It's proportional, it has no constant, that's why the line will pass through origin. This is stress versus strain graph within elastic limit. Stress strain graph within elastic limit. Okay? So this constant which we have defined above, this constant defined above is known as modulus of elasticity or coefficient of elasticity. Coefficient of so why object shows elasticity? Have you ever thought of it? Why it will come back to its original state? You think with the concept you already got. Actually some models are there which is nowadays excluded from CBSE syllabus, that spring ball model. If the spring is stretched and the deforming force removed, it will come back to its original state. or if it is compressed and external deforming force is removed, it will regain its original shape and configuration back. This is one model. Is there any other concept to explain elasticity? It will neither remain in reduced state nor will go for elongated state. Why? You think in energy point of view that how it can be answered. I will definitely answer next class. Achha, modulus of elasticity or coefficient of elasticity, we can define it for this thing now. Longitudinal stress versus longitudinal strain. Let us define here. So in this case, what is stress? F by A. What is strain? Delta L by L. So tell what will be the modulus of elasticity here? Modulus of elasticity in case of tensile force y equal to F by A divided by delta L by L, isn't it? This is called Young's modulus. Okay, so Young's modulus has this value F into L by A into delta L. Clear? What is the unit of modulus of elasticity? Unit of Y will be unit of F by A only. That is Newton per meter square. In general, we write E, modulus of elasticity. But in case of longitudinal stress or strain, we will write Y. Okay? So this is unit of Y. Unit of Y is what then? Newton per meter square. Let us go for this thing. In case of volume stress and volume strain, I hope all of you remember what is volume stress. Volume stress is what? Increase in pressure. Volume strain is what? Decrease in volume by original volume. So how to write elastic modulus in this case? I am writing here. The same experiment. Ball is taken at certain depth and it is taken at greater depth. Then this was the volume V. At greater depth it becomes V minus delta V. That volume of the ball, it is smaller now. So volume strain is what? Here pressure is P. At this depth pressure is P. Here pressure will be what? P plus del P. Isn't it? Here pressure is P plus del P. So K or kappa, don't say K, it is kappa, that is called bulk modulus. How to define it? It is del P by del V by V, but minus sign you have to take before. Why? As increase in pressure will decrease the volume, isn't it? If you increase pressure, volume will be decreased. Del P, it becomes del V by V. So ratio of these two is known as bulk modulus. We are defining all these things. We will be working on it with many examples. Okay, but first you know volume stress versus volume strain you have understood. Now the third one, shearing stress versus shearing strain. Go for that. This thing. How to define modulus of rigidity here? Here the elastic modulus has a special name that is called modulus of rigidity. What is that? Modulus of rigidity. Same definition. Modulus of rigidity eta equal to, or n, whatever you say. This is stress by strain. What is stress? Stress is longitudinal. I told you earlier, it is F by A that divided by theta. And again I remind you, theta should be expressed in radian. Okay? Theta should be given in radian. So eta will be F by A that divided by theta. Clear? This is modulus of rigidity. Now, graphically, let us observe some things which will help you to study elastic behavior, and then we will be solving some numerical problems based on it. Stress versus strain curve. Okay, just draw the curve, then I am going to explain different parts of it. Yes, it becomes thinner and thinner. It's my choice. I have given this one. You can change the shape, no problem. Finally, it snaps here. The distance between these two long for ductile substances, for brittle substances, distance between C and D is less. Just draw the diagram, then I will explain the parts. So, what do you observe in this graph? From O to A, this is elastic region. What is the meaning of this thing? In this elastic region, if we ever remove the load, the substance regain its original shape and configuration. Okay, you can text also. If you ever remove the load, the substance regain its original shape and configuration back. Okay, so this will represent the elastic limit. This one is the elastic limit. Okay. From A to B, this region is not complete. Let me explain this part again. Just if you do the experiment, you go on increasing the load, then up to certain value, if you remove the load, you are increasing very small amount the load. Increment is also small. Up to certain limit, we will observe that the suspended string wire will show elastic behavior if the external force, I mean load, is removed. But beyond it, what will happen? If we increase the load, the way I was telling you, when the rubber band you are increasing its length, it can recover the original shape and configuration back up to certain limit, but beyond it, it won't. So what will happen then? Do you think that it has lost its elastic behavior fully? No. So region from A to B actually depend in this graph, in different books given different manner, and the way they have performed the experiment, it depend on that, but it will never go down, it will be steeper always. Okay, A to B, this region is both elastic and plastic. Both elastic and plastic. It means what? Between these 2 points, if we ever remove, it means if the load is ever removed, this point be P, from where we are removing it. Okay, if we ever remove the load from the point P, if the load is ever removed, then a permanent set or strain is observed in it. Why? How it is? See this diagram. At the point P we have removed. It is trying to get zero stress. Stress is reduced to zero, but a permanent strain is developed over there. You understand what I said? O to M, a permanent set or strain will be there. This set or strain is permanent. You cannot remove it. Got it? Like rubber band, you are increasing the length. But at certain instant, if you remove the load, it will not get back to original state. Small stress or strain is small strain is produced in it, but that is permanent. You cannot remove it. No process will help you to get back the original shape and configuration back. This point B will be referred as yield point. This point B Point B will be referred as yield point. What is that yield point? Because the substance at B, it has yielded towards its elastic behavior. Okay, it has yielded towards its elastic behavior. Clear? Beyond the point B, this region is plastic region. In case of wire, it becomes thinner and thinner. Okay? This point, even you are not applying, suppose you have reached the point B by applying a force 100 Newton. Okay? Then permanent set or strain is there. Then from the point B, you are reducing the force. You got back to, you have reduced the force to 0. Then you start afresh. You have applied only 50 Newton. Then you will see that it is being elongated from there only. For that much elongation, you have applied greater force. But once the permanent set or strain developed, then this plastic region, what will happen? Even a small quantity of force is applied, it go on elongating or compressing. Okay? Even a small force is applied, you will observe elongation or compression. That is permanent. If we are assuming that it is being elongated. At the point C, from the point C, better to say, it start becoming thinner and thinner. At the point D, it finally snaps. This D is referred as fracture point. This D will be referred as fracture point. At fracture point, it snaps. Okay? This is the stress strain graph. You should remember every part of it for your school based exam or for JEE exam also. Okay. Now we are going to calculate, then we will come back to, we are going to calculate something, we will come back to the graph then again. Let us know what is elastic potential energy. We have done it probably. Elastic potential energy is did in case of spring, half kx square, isn't it? But here we will do it for string mainly, remembering the fact for spring also. So elastic potential energy. This is also the case of within elastic limit. Okay. Let us calculate it for a string. We will simply write EP stored in a string. Not going to do it for a spring. For spring, you must have seen that it is half kx square in work energy power chapter. Okay. So EP stored in a string will be how much? We are going to calculate. We are going to prove that EP stored per unit volume. To prove that EP stored per unit volume is equal to half stress multiplied by strain. EP stored per unit volume is half stress into strain. Okay. This one is a string. tied here on the wall. It's everything will define. What to define? L, A and Y. L is length, A is area of cross section and Y is the Young's modulus. Okay. Suppose its length is, this is the initial position of the string. This is the initial case. Now, length is increased by x and we are assuming A and Y. Y is intrinsic property, it will not change. Area is not changed considerably. Okay. And finally, suppose same string, we are doing the experiment on the same string. Finally, its length is increased to small l. Similar is the case for compression also. Okay, we can compress also. Now, when elongation is x, what is the force developed against elongation? You know, you are applying, you have to apply some external force to elongate, no? So stress will be produced. That force, if I have applied this manner, force against elongation will be the same. How much force? When elongation is x, how much force is there? Force acting against the elongation we have applied force F, but we cannot account for that. We are accounting for the internal force of reaction. It is easier for us in terms of Y, A and L. Okay, force acting against the elongation. We have to find this. Y equal to F by A, X by L. This we know. Elongation by original length. I hope you all remember. So this is A into X. What is the value of F here? Y Ax by L. Isn't it? Force is Y Ax by L. Isn't it? Clear? What you have to do there? Final elongation is how much? Small l. But here elongation is x. This much force is acting against the elongation. And you know, work is done by the force along elongation, along the displacement, that work is positive. So external force go on increasing its length. So after this step, to increase the length further by dx, I mean it was at P, now we are increasing the length by PQ equal to dx. To increase the length by dx, amount of work done will be F into dx. Yx by L into dx. Am I correct? To increase the length by dx, amount of work done will be F into dx, that is Yx by L into dx. Clear? Total work done how much? This is dW, and there is no confusion in it. Work per energy, I told you, if the object is displaced along the direction of force applied, then that work is positive. So total work done to increase the length by L will be W equal to integration 0 to L yx by L into dx, isn't it? So this you write y, a, L, all these are constants, 0 to L x dx, ya by L, and this will be x square by 2 0 to L, upper limit minus lower limit, this we got finally, W equal to this. So this work done will be stored in the where, in this where, this work done is stored in the where as its potential energy. Therefore, EP equal to YA, we can take big U for this, YA L square by twice L. So EP per unit volume will be what? Per unit volume will be what? Small u. Small u is what? U by A into L. So YA L square, that divided by 12 AL. Check. I am just calculating. So small u equal to half y. Oh, this is A into capital L. Extremely sorry for that, because total volume of the wire is not A into L. It is A into big L. So this is going to be half y L square by L square. Now stress is what? Stress will be what? F by A. Stress is F by A. See this expression? In the final position, F equal to AYL by L. So F by A how much? YL by L. So you write half YL by L into L by L. So small u equal to half into stress this multiplied by strain. Clear? So U is equal to half stress into strain. Okay, done. Elastic potential energy stored in the wire is given by half stress into strain. Done. Now we will finish this session by discussing one more point from stress strain graph. Here, if I tell you, you will present the elastic potential energy part in diagrammatically. In this diagram, which part will represent elastic potential energy? It's a conceptual question. You know that work done within elastic limit, that potential energy within elastic limit only. So in this graph, which portion will represent the work done per unit volume? Let me explain. You draw a perpendicular here. This is the perpendicular, AL is the perpendicular. Now tell me area of this portion. Area of this triangle is what? Area of triangle OLA half into OL into AL. You agree or not? OL means what? Strain. AL means what? Stress. Half into strain into stress. Okay? So this is the geometrical or graphical presentation of work done per unit volume for a wear. Clear? I hope you have understood this. Advanced concept is definitely there, that I'll discuss later on. First, you should work on it. What you have understood.